Hello, now we're going to do solutions to the problems assigned out of section 4.3. So first we are asked to find the domain of a rational function. Remember, a rational function is of the form a polynomial divided by a polynomial. Now, the domain of a polynomial is all real numbers. However, a rational function may have this quotient, in which case you don't want to divide by 0. So there's no obstruction to plugging any x into the numerator, and there's no obstruction to plugging any x into the denominator unless it evaluates to 0, which means the domain of any rational function where it's expressed as a polynomial over a polynomial, not plus something else, okay? The domain is always going to be all x except where the denominator is 0. So in this particular case, it's all x except where x minus 4 times x plus 5 is equal to 0. In other words, it's all x except x equals 4 and x equals minus 5. And typically we would write this as all x so that x is not equal to 4 and x is not equal to minus 5. So down here is our set notation for all of the x's that are not 4, nor are they minus 5. Next up, find the domain of this rational function. So again, we have a polynomial divided by a polynomial, which means the domain is all x except where the denominator is 0. In this case, we would have x squared equals negative 8, which has no solutions. You cannot have a square be negative 8, which means the domain is all numbers, all real numbers at least. So because there are no real x's for which the denominator will be 0, the domain is all numbers. Referring to the graph below, okay, try to find the domain and range. So first of all, the domain is all x's that can be plugged in, and it appears that this value of x right here does not produce any sort of output. So the domain is all x except for this one. And this x appears to be 2, just based on looking at the graph. Now the range is all possible y values that can be gotten out, and this particular y value is marked off as a horizontal asymptote, which is never actually achieved by the rational function. Sometimes rational functions can eventually, or at certain times I should say, be equal to their horizontal asymptote, but this one does not appear to have this behavior. We're really just using the graph to make an educated guess. So all y values above this line can be achieved. Specifically, here are y values slightly larger, and as we go along this vertical asymptote, we achieve all the y values up here. And here we have y values slightly less and all the ones below it. The only y value that isn't achieved is that dotted red line, which appears to be about negative 3, okay, just by looking at the graph. Okay. Now we are asked to find any intercepts. Okay, so if we plug in x equals 0, we would get out the y-intercept. Plugging in x equals 0 is this line right here, which intercepts the graph right there, and that appears to be y equals 0. The x-intercept would be set y equal to 0. And in this particular picture, the y equals 0 line also intercepts the graph exactly at this one point we already found. Okay, remember, y equals 0 is the x-axis and x equals 0 is the y-axis, both of which intersect on the graph. Okay, this is not always going to happen, but in this case, the y-intercept is y equals 0 and the x-intercept is x equals 0. To find horizontal asymptotes, okay, this one right here is pretty much the only horizontal asymptote given to us. Asymptote, remember, means something that the graph is approaching as x goes to infinity or as x approaches a certain specific value. But it's a line that is something that the graph gets close to. Okay, now this horizontal line that the graph appears to be getting close to is just y equals minus 3. That's the only horizontal asymptote that seems to be on this graph. The only vertical asymptote, in other words, a vertical line that the graph gets close to, is this one down here, and that was x equals 2. Notice the relationship between the domain lining up to vertical asymptotes and the range lining up to horizontal asymptotes. This isn't necessarily guaranteed. Okay? It is possible to have a point excluded from the domain that is not a vertical asymptote, and it is possible to have a point excluded from the range that isn't a horizontal asymptote, it's possible to have a horizontal asymptote that isn't actually excluded from the range. So don't leap to any conclusions here, but this is something that will frequently line up. Oblique asymptotes, there are none. If there is a horizontal asymptote, there is not an oblique asymptote, and if there is an oblique asymptote, there is not a horizontal one. So between these two questions about finding horizontal and oblique asymptotes, you will always be doing one of them, but not the other. So there are none for this picture. Okay, moving on. Similar, okay, we are asked to find the domain and range. So the domain is all x except these two, which appear to be values of x that do not correspond to any y value. So it's all x that are not equal to -2 or 2. Okay, the range, well, the red dotted line at y equals -2, okay, notice that here we get everything below that, and here we get everything below that. What about values above -2? Well, here we don't actually come all the way down. In fact, it appears the range only gets as low as -1 and then goes up. So here we see that the range appears to be everything below -2, but not including -2. That's each of these branches. It's all the y values below -2, but it doesn't appear to actually reach it. This branch of the function here starts at -1, and it appears that it does reach that value, and then everything above that. However, -1 is included in the range because it appears to be achieved right there, but nothing in between -1 and -2 is in the range. And this is something that can happen. Okay? The points to be excluded from the range aren't just horizontal asymptotes, as we mentioned in the previous problem. It will frequently line up that way, but it is not guaranteed. Intercepts. So the y-intercept is found by plugging in x equals 0, which is right there at that point that we've already labeled, and that appears to be a height of y equals -1. Similarly, x-intercept is solved by setting y equal to 0, and there appear to be 2 points about here and here. Now, it's not terribly clear from the picture what those x values are, but it's maybe -1.5 and +1.5. We're really just looking at the graph and trying to make an educated guess. So if I erase these points, you know, they don't actually appear to be halfway there, so maybe -1.33 and +1.33. It's not immediately obvious. But maybe x equals 1/3, 1 and 1/3, I'm sorry, or x equals -1 and 1/3. I'm putting a question mark here. We're really just making an educated guess based off the graph. Any horizontal asymptotes? Well, this one right here is the only horizontal asymptote that really seems to make any sense on this graph, and that's just y equals -2. Vertical asymptotes, there are two labeled. We've already discussed them, x equals 2 and x equals -2. These two things down here. Finally, oblique asymptotes. Well, as mentioned, either you have horizontal asymptote or you will have oblique asymptotes for rational functions, but not both. So there are no oblique asymptotes in this picture. Okay, moving on. Here we don't have the graph, but we do have the function. Find vertical, horizontal, oblique asymptotes. So the first thing we have to do is ask, is this a rational function? In other words, does it look like a polynomial over a polynomial? Well, 7x is a polynomial of degree 1, and x plus 4 is a polynomial of degree 1. Then we ask, is it reduced? In other words, is there a factor shared between the numerator and denominator? Well, these are just degree 1 polynomials. They are already factored. Okay? The only root of the numerator is x equals 0. The only root of the denominator is x equals -4. There are no shared roots between those polynomials, which means there's no shared factors. So yes, this is already reduced. Once you know you have a rational function that is of the form polynomial over polynomial, and it is in reduced form, vertical asymptotes are achieved just by setting the denominator equal to 0. So x plus 4 equals 0, or x equals -4 is going to be the only vertical asymptote. Horizontal asymptotes, or oblique asymptotes. Now remember, you're only going to have one of them, but not both. So we ask, what's bigger, the degree of the numerator versus the degree of the denominator? And there are three possibilities. The degree of the numerator can be smaller than the degree of the denominator, in which case you have a horizontal asymptote of y equals 0. The degree of the numerator can equal the degree of the denominator, in which case you have a horizontal asymptote given by y is equal to the ratio of leading coefficients. So each of the numerator and denominator is a polynomial, so each of them have a leading coefficient. That's the number multiplying the largest power of x. And you would just take that ratio. Or the degree of the numerator is larger than the degree of the denominator, in which case you have an oblique asymptote, and you have to find it with long division. So which situation do we find ourselves in this problem? The numerator is 7x, the highest power of x is 1. That is a degree 1 polynomial. The denominator is x plus 4. That is the highest power is just x, that is a degree 1 polynomial. So the two degrees are equal, which means the horizontal asymptote is given by the ratio of the leading coefficients. So the leading coefficient of the numerator is the number multiplying x, because x is the largest power that I see. So the leading coefficient in the numerator is 7. The leading coefficient in the denominator will be the number multiplying the largest power of x down there. The largest power of x I see is just x, and what number is multiplying it? 1. So the only horizontal asymptote is given by y equals 7 over 1, or just 7. Okay, this technique of using the leading coefficients is only used, remember, when the degree of the numerator is equal to the degree of the denominator. So we found horizontal and we found vertical asymptotes. There are no oblique asymptotes because there was a horizontal one. All right, moving on. Here, find all vertical, horizontal, and oblique asymptotes. So, is this of the form one polynomial over another polynomial? Yes, it is. Okay. Is it reduced? Are there any shared roots or zeros between the numerator and denominator? Well, the numerator only has the 0, x equals 0. The denominator has roots x equals 3 and x equals minus 3. There are no shared roots, which means it is in reduced form. Okay? If there are no shared roots, then there are no shared factors. In other words, there is not a factor that I can cancel out of both. Now that I know it is in reduced form, vertical asymptotes are given by the roots of the denominator, and we just found them. Okay. How do I find if there are horizontal or oblique asymptotes? Remember, there's only going to be one of them, and the question becomes, what's the degree of the numerator versus the degree of the denominator? Well, the numerator has degree 3, and the denominator has degree 4. When the numerator has smaller degree, the horizontal asymptote will always simply be y equals 0. So we can see this by saying, what happens when x is really, really big? X cubed is really, really big, but x to the 4th is even bigger, because whatever x cubed is, you multiply it by x again to get x to the 4th. So if x cubed is enormous, x to the 4th is x cubed times x, which is even more enormous. So since the denominator is so much bigger than the numerator, even though the numerator is big, when you divide it by something much, much bigger, that is very close to 0. Okay, so when the degree of the numerator is smaller than the degree of the denominator, you will end up with larger powers down in the denominator, so you are dividing by larger powers, you are going to 0. And again, there are no oblique asymptotes because there was a horizontal one.